we have a pi product problem that amounts to a super large number, and we're trying to reduce it modulo 24. So I'm just going to write out some of the terms here. 5 to the 21st, and this is product notation, not summation notation. So this would be 5 to the 21st, 7 to the 21st. Let's just write out a few of them. 11 to the 21st, that's the next prime. We'll include the customary ellipse here, ellipsis. And what are the last? We're going up to 31, so we can write down 29. Of course, there's some that I'm leaving out. All right, so like this. So you can see just one of them is such a large number you can't pronounce it, right? But we want to know what this huge number is, modulo 24. And what that means is if you divide 24 into this unpronounceable number, what is its remainder? It's guaranteed to be between 0 and 23. Okay, an integer between 0 and 23. If it happened to be a multiple of 23, the remainder would be 0, of course. So you can see what I've got going on here. 5 to the 21st, 7 to the 21st, 11, missing terms all the way out, okay? Now, laws of exponents gives us this circumstance right here, okay? It's kind of like the distributive property of exponents, but we have all the primes, 5, 7, 11, 13, 17, 19, 23, 29, 31, all raised to the 21st power. All right, again, what good is that? Well, the laws of modular arithmetic indicate that we can reduce each of these guys, each of the greened out numbers right here. We can reduce, when I say reduce, find the remainders when you divide by 24, okay? Now, there's all kinds of ways to do this. I chose to go this route. If you'll take a look here, what I've done, 31 is congruent to 7 right here. You can see why I have the 31 here. And I'll just write it out. 31 is congruent to 7. And the nice thing about modular arithmetic, it behaves in very much like regular equality. 31 minus 7 is 24, right? Now 29, in a similar fashion, 29 is congruent to 5. Okay? 29 minus 5 is 24. And then we got a negative going on here because it turns out that's kind of convenient. 23 minus a negative 1, or the difference between 23 and negative 1 is just 24. So you can see how 23, 29, and 31 got replaced by minus 1, 5, and 7, smaller numbers, if you will. Okay? Now the rest of this, I'll try not to talk about every last step, but I continue with the reduction process right here. I just brought the minus sign around to the front, and hopefully you guys can follow the reductions that I've done all the way through the problem. Notice that right here, 240, we get 247 when we multiply. Let's see, 13 or 17. 13 times 19 is 247, and you see how I left the 17 here. 13 times 19 is 247, and notice that 247, by inspection almost, is congruent to 7. Okay, and again, modulo 24, 247 minus 7 is 240, clearly divisible by 24. All right, and so now at this stage right here, we're left with that this 7 is this 7 that you see right here. Now, notice that 7 times 17 is 119. Okay. And again, that is congruent to a, quote, a small negative number. It's actually a large negative number. But you see how this negative 1 comes in? And so this works out very nice because we just get 11 out of this. Very, very useful information, okay? Again, hopefully you followed all these steps. I made up my mind I wasn't going to go through every last detail, but this large number reduces to 11 modulo 24, okay? Now let's keep going. So our original problem just becomes 11 to the 21st, okay? Now there's another important result. This is still a large number. You're going, well, what are we going to do about this, 11 to the 21st, modulo 24. Well, it turns out we have a very handy result here. We have p squared, where p is a prime. It's always congruent to 1 mod 24. Now, this is actually a proof I've done. You may have seen it in an abstract algebra book, but it follows from the fact that any odd number is congruent to 8. Okay, any odd number, and P is going to be an odd prime here, right? So any odd number, independent of it being prime, is congruent to 8, mod 24. And also any odd prime greater than or equal to 5 is always going to be congruent to 3, mod 24. And that's something that's not hard to prove. So I'm just going to state this as a fact. P squared is congruent to 1 modulo 24. So we can rewrite this as 11. 11 is a prime number. Okay, so we can write this as 11 squared raised to the 10th power times 11. Okay? And you can see the utility of that, folks. We're taking advantage of the fact that P squared is congruent to 1. So this would be congruent to just 1, you see, raised to the 10th power, which is always good news. Okay? Times 11, which is equal to 11. And that completes the demonstration here. Okay, that's it, folks. The whole thing reduces to 11 modulo 24. And you may want to let me know if you saw a quicker way to do some of this reduction right here, or just a quicker way overall. But that's it. So thanks for viewing.